Hi and welcome to my video on trees and connector problems, and this is the first video of Unit 4 Topic 3 which is networks and graphs, and really it's a follow-on from from Topic 2, which was just graph theory. So first of all, there's a learning goal there, and now let's talk a little bit about trees and minimum spanning trees and then some connector problems. So a reminder, first of all, we talked about this in graph theory. A tree is a graph where no loops or cycles exist. Now I've kind of written this loose definition underneath where I've made the statement that each vertex is only accessible on one path, and it's not fully true, and so I want to explain myself now. So the point here is that each vertex is connected to the graph in one way. And so I've got a little bit of an example here. It's very brief. But basically, you can see that first one I'm claiming is a tree. The second one is not a tree. Now, if we have a closer look, we can see that due to this additional edge here, we've created a cycle. So it's not a loop, it's a cycle, because you can do this sort of triangle shape. We've created another face. So if there's a face, well, that's an issue. That means it's not a tree. This one here doesn't have that face. And so D is connected to 4 paths. It's kind of that central point, but it's still a tree because each path is connected along, or vertex is connected along one path, with D being that kind of central point that connects the whole tree together. So this is a tree, whereas the second one is not a tree. And so your main thing you're looking for are cycles or loops, which would be like that. A spanning tree connects all vertices. So we have a spanning tree, that original example, and the second one here, you can see that vertex G is not connected, so it's not a spanning tree. So a spanning tree is connected because all the vertices are connected. And if a spanning tree has n vertices, well, then it must have n minus 1 edges. Think of it like this. If I start with this one here and I connect A and C, that's 2 vertices connected by 1 edge. And each time I want to add an additional vertice, I have to add an additional edge. So I always end up being 1 vertice ahead of the number of edges that I have. So in this case, I've got 7 vertices and 6 edges. So a spanning tree will always have n vertices and then 1 less edge. And that's another way you can verify if it's a spanning tree, particularly if you're not given it in a graph form. Minimum spanning trees are spanning trees that require the minimum weight or the minimum distance or time or something like that. And we're going to spend a lot of time on that today, so I'll take this further now. In life, we're often trying to reduce time, cost, distance, and so contextually, finding a minimum spanning tree in a larger graph is going to be really important to us. So let's have a look at an example here. In orange, you can see that I've got 4 towns because I've got a distance map. So they might be towns, they might be something else, but let's say that they're towns. And these 4 towns have got distances between them. They're connected by 5 edges. 4 towns, 5 edges. This is not a spanning tree. There's too many edges. And you can see that there are 2 faces formed. And so there are multiple cycles here, etc., etc. What we're going to try and do is find the minimum spanning tree. So the shortest path through this graph that connects all towns. In this case, the 4 vertices, there are 4 vertices, 4 towns, and so the minimum spanning tree will have to have 3 edges because we know there's always 1 less. So let's determine a minimum spanning tree. So what I'm going to do, and this is sort of a roundabout way, we're going to get to a bit of an easier way, but I'm going to go ahead and assume that 5 will be part of our minimum spanning tree because that is our smallest distance, our shortest distance there. Now, I reckon that 7 might be part of our minimum spanning tree. And remember, our minimum spanning tree has to be no cycles created, has to connect all vertices. And so I could connect Nuptial using the 11 kilometre one to Cantal, but I'm going to connect it to Rugo because that's only 10 kilometres. And so this looks like my minimum spanning tree, the 10, the 7 and the 5. And an example here might be perhaps you're a postman and you need to travel between these 4 towns and you want to make sure that you do it in the shortest possible time or distance. And this would be a solution to that. Obviously, there are problems formed here. What happens if you start in Rugo? Well, then you go to Nuptial, and then going back to Rugo would be a waste of time, so we might include the 11 kilometre band there. What happens if you need to start and finish in the same point? So there are additional problems here, but this is the minimum spanning tree for this graph. What if a new underground wormhole suggested there? New passage was found from Nuptial to Amblew. So let's say I'll draw that on there. So Nuptial around to Amblew. What is the maximum distance that it could have to determine a new minimum spanning tree? So at the moment, we've got a minimum spanning tree, but as you can see here, if I was able to go from Nuptial to Amblew, I could cut out one of the other edges. So I could, for example, go Rugo, Nuptial, Amblew, Cantel like that and cut out that 7 kilometre edge. But the obvious answer here is why not cut out the biggest edge, this 10 kilometre edge. So if Nuptial was anything less than 10 kilometres, well, that would benefit us. That would create a new minimum standing tree. So 10 kilometres would create an equivalent minimum spanning tree. So we say anything less than 10 kilometres would be a new minimum spanning tree. Now that particular question, well, that's a little bit beyond what you'll probably see in the textbook, but that's what you can expect to pop up as a complex familiar type question, maybe a trickier sort of multiple choice question in your external exam. So there you have it. That's our intro to minimum spanning trees, spanning trees, all that kind of stuff. And you're now fully capable of getting on to exercise 11A, question 1 to 4. Obviously read the examples and the textbook information. It's slightly different to this, and that's done deliberately, so you've got that multiple resource, and ask your questions of your teacher as required. All the best.